Good morning, everyone. Today we have our last Cine webinar of this year. Today our speaker is Professor Yury Gogotsi. I'm very pleased to introduce Professor Gogotsi. Professor Gogotsi is a global scientist born in Ukraine, trained in Western Europe and Japan, whose research focus primarily on nanomaterials, materials chemistry, and electrochemistry. He currently works as a chaired distinguished university professor and director of the A.J. Drexel Nanomaterials Institute at Drexel University in Philadelphia, United States. Here, he received several awards by the development of carbide-derived carbons with tunable porosity, discovery of new carbon nanostructures, visualization of liquids in carbon nanotubes, and the discovery of MXenes and development of materials for electrochemical capacitors. His papers have been cited more than 15,000 times, and he has a age factor around 200. Today, Professor Gogotsi will talk about electrochemistry of MXenes, Redox capable 2D materials for energy storage and conversion. Professor Gogotsi, please, the floor is yours.
Thank you very much. Thank you for this invitation. I'm delighted to be here, even though I would prefer to be in Brazil in person. I think I'm also lucky I'm giving my seminar today, not tomorrow, because tomorrow entire Brazil will be preparing to watch the next game in the World Championship, and I wish Brazil win. I predict Brazil to become champion this year, so good luck. But today, let's talk about science, about new materials. And I'm going to describe today MXenes, materials which were discovered at Drexel University, but by our group with a colleague, Professor Michel Barzoum, our student, Michael Nagib. For people who are new to the field, those are two-dimensional materials, so it means that they have very thin nanometer or thinner layers with just a couple of atoms in cross-section, but large lateral dimensions. So if you look at the structures in the cover slide, red dots are transition metal, titanium, moly, niobium. Small black dots, carbon, nitrogen, can be oxygen substituting here. Those are materials which we call MXenes, and they come in a variety of structures. They come variety of properties, including plasmonic colors you can see here. And today, I will introduce you to that field. I will talk about materials in that area in general, their manufacturing, processing, and also I will describe energy storage and talk a little bit at the end about some of the energy conversion applications to give you an idea of where, how, and why MXenes can be used and outperform or complement other materials here. But first, probably something that doesn't really need long discussion. It's a sustainability, energy, very big issue. Has been for many reasons, starting from global climate change. I don't really like the word global warming because if it becomes warmer in one place, it may be colder in another place. It's related to geopolitical situation in the world when Russia is using oil and gas to pretty much put pressure on Europe and decrease support of war that they can capture in independent country in their neighborhood, and simply just to keep air around clean and make our cities less polluted here. And of course, a large role in this game play nanomaterials. I will explain a little bit later why, but just a few things to note. If we had sufficient technologies to solve the problem, it had already been solved. New materials offer new opportunities. They can do things that existing materials can't. And that's why development of materials is important. And if we want to have catalytic application, we need high surface area. If we want to have fast charging of our electric cars, we need to eliminate solid state diffusion. For those and many other reasons, nanomaterials start playing an increasing role here. And among those, the key role really belongs to two-dimensional materials. You may recognize these two gentlemen, Andrei Geim and Kostya Novoselov, who received more than a decade ago already Nobel Prize for discovery of interesting physics in graphene. But probably not everyone knows that in addition to graphene, there are already dozens of other materials discovered. And if you look at this, for example, scale, you will see that they range from dielectric materials, wide band gap, like hexagonal boron nitride, to many semiconductors, semi-metals, and even metals. This is exactly what MXenes, like titanium 332, the first one discovered using, brought here. Why 2D materials? Because you can use them as building block, like bricks in a wall or Lego stone, to build dense, well-packed structures with high mechanical properties, but properties not a bulk something, properties that we can pretty much program by taking different 2D layers, combining them together here. For example, taking a metallic material as a current collector, semiconducting metallic materials as active layer in a battery, say, dielectric 2D materials like boron nitride as separator, and pretty much build an entire device. So really, while for a long time, focus has been on graphene before carbon nanotubes, we're really moving from this single wonder materials that some people claim change the world to having building blocks to create new assembled nano-architectured materials and devices which will define future advanced technologies. This is what we are trying to do in my laboratory. And to do this, to achieve this, we need all these building blocks that I showed you before with all this variety of properties. You cannot build device if you don't have metal. You cannot build device if you don't have semiconductor with required band gap, and so on here. So MXenes played a special role here. And actually, I will try to convince you that they can be used for energy harvesting and storage, among many other applications, but there are many other applications I'm not going to discuss today. Materials are relatively new. They were discovered at Drexel just a little bit more than a decade ago. So what do we have in this family of materials? As you could already see on my cover slide, there are several structures possible with from 2 to 5 layers of transition metal connected to by 4 or 1 in the Cine structure layer of carbon and nitrogen. Oxygen can also be in that position. We have a dozen of transition metals possible, this one marked in green. Also, rare earth metal can be components of MXenes as well. But what is also important, if you have a transition metal, its surface environment will not stay pristine. Transition metals gladly share electrons with other elements, and oxygen, hydroxyl group, amides, amines, and chalcogens and halogens can all be terminating the surface of MXene, forming something we mark it T. T stands for surface termination, X for carbon and nitrogen, M for earlier transition metal. So it's a MXenes, and suffix in stands to show their two-dimensionality, like graphene, silicene, borofene, and other 2D materials. Moreover, in this family of materials, we have already showed our ability to do engineering of materials at the atomistic scale. For example, we can have not only these structures with different numbers of layers of transition metal. We can also make atomic sandwiches out of plain ordered MXenes, where one metal is on the surface, for example, moly, which will determine electrochemical, chemical, catalytic properties. But another layer is in the middle, for example, will be titanium, which will determine conductivity, which will act as a transport of electron highway, because conductivity of these materials, majority of them are metallic, jumping ahead, is determined by the elements of transition metals. But we can also make in-plane ordered material with alternating atomic columns of different elements. Maybe better to see in the cross-section. And those elements, if those are rare earth metal, for example, or yttrium, scandium, they can be etched away, leaving lines of divergences. And we can build also solid solutions on X side, carbon nitrides, but also on M side, as shown here, like metal alloys. And if you take 3 to 5 transition metals, you can get high entropy multi-elemental MXenes. And of course, don't forget about surface termination. So pretty much what we show nowadays, we push nanotechnology to a level we can truly design 2D materials with a huge variety of properties here. And every year since the discovery of titanium 3C2, which was done by Michael Nagib, PhD student at Drexel, currently professor at Tulane University, produced the first one. Every year, more and more and more MXenes have been added. Last year, we celebrated 10 years from discovery of first MXene. There was a special issue of advanced materials from where I take it here. But today, we have already at least 54 published different MXene structures among all these groups of materials. The ones that are semi-transparent are still to be produced. No representatives have been made yet in those systems here. But if you do the math, take a dozen of transition metal, multiply by carbon or nitrogen, and 4 different, like a structure number of layers, just here, you end up with about 100 of simple stoichiometric compounds. Take different 10 surface termination I showed to you. It's already 1,000 of stoichiometric compositions possible. But with all these diverse designer structures, with all the elements possible, solid solution, it's virtually infinite number of new two-dimensional structured compositions possible. So one thing MXene brought, it's enormous diversity. Yes, we need, of course, to do DFT simulation. We need to use artificial intelligence to select materials with the right properties for application. But we can design them, we can do synthesis of those materials on demand. And this is a big thing. The next thing, great to have theoretically many, many different materials, but can we make them? Can we make them in large quantities? And the idea is here that these materials are produced by wet chemical etching or emulsion salt etching, I'm not going to talk about today, or other extractive synthesis. Like we made carbide-derived carbons from carbide before, taking transition metal or silicon boron atoms from carbides. We take layered carbides, which are known max phases. They are not only ones. And we remove from these carbides by etching in either acid, emulsion salt, halogens, electrochemical etching, monatomic layer of element, for example, aluminum. So if you take moly, for example, titanium 3 aluminum C2 carbide with this structure with layers of aluminum connecting layers of carbide. Remove it away, we get weak bonding now. Instead of strong metallic bonds, we get weak van der Waals bonds. We get something looking like vermiculite clay or thermally expanded graphite. It becomes MXene. You see carbide. Aluminum is gone. Surface termination appeared on the surface, and we get this material. And now we have weakly bonded layers, which can be delaminated into single layer flakes. Moreover, great to have a very large number of materials. Be able to do synthesis by etching here. If you want to make it practical, especially for electrochemical applications we are discussing today, we need materials that can be produced in large quantities, materials from abundant precursors. And actually, if you look at majority of first MXene discovered, titanium-based MXene, titanium 3C2, titanium 2C, carbon nitrides, titanium, carbon, nitrogen among the most abundant elements in plentiful supply. Surface termination, oxygen, fluorine, chlorine, sulfur as well. Aluminum, vegetable waste too. But vanadium, zirconium, niobium, moly, other very common MXene elements here are also not far away, available. We don't have limitation in supply of those materials potentially here. So again, they can be made of abundant elements here. Now, great to be able to have many new materials. There are quite a few already available to us. It's great to be able to produce them in quantities, but does anyone need them? People look for properties, specific properties that other materials don't provide. And one of them is high metallic electric conductiviity of MXenes. If you take the single layer flakes, which look very much like flakes of graphene or moly disulfide or other materials, they're single crystalline, as you can see from selected area diffraction, high resolution TEM. And make a film, like a paper, like a graphene paper. You might have seen it, very popular material right now made from reduced graphene oxide. You can get conductivity, actually nowadays we get over 20,000 Siemens per centimeter. Just for comparison, similar paper produced by reducing graphene oxide will have 10 times lower conductivity, in spite graphene being always praised for its high conductivity. And the reason is that graphene is a zero band gap semiconductor. You need to create defects, dope it to produce carriers. Majority of MXenes are true two-dimensional metals with a high density of states at the Fermi level, high concentration of carriers. But they're very unusual metals. They have oxide-like or hydroxide-like or collagen-like polar hydrophilic surfaces. So you can look at them as conducting clay or water-soluble two-dimensional metal. No other material combines those properties. Again, take graphene as the most common, best known 2D materials. Pure graphene is hydrophobic, cannot be dispersed in water, cannot be processed from aqueous solutions. People oxidize it in acid, make graphene oxide, process it, and after that reduce to benefit from conductivity. MXene has both properties in one material. Moreover, they're actually stronger and stiffer than all other solution processed material. Ideal flake of graphene, if you take it here, will have higher tensile strengths. But no one makes composites or battery electrodes or current collectors from perfect single crystal graphene produced by peeling off from large crystal or CVD. People do it from graphene plate with graphene oxides. And MXenes are stronger. You can see here 20 micron roughly flakes of titanium 3C2. You will never find single layer. Those are single layer flakes produced from solution deposited on silicon wafer. You will never see flakes of that size of oxide or moly disulfide, for example. They will just break from vibrations when you process them here. MXenes survive because extreme strengths. But moreover, unlike graphene, it comes not only in shades of gray, those are plasmonic materials with a variety of colors that you could see in the first slide that I showed to you here. And there are many other useful properties like light to heat conversion and others used, for example, for water desalination, sensing, surface against Raman spectroscopy, and so on. But the key thing is here, all these properties can be controlled by selecting the right composition as I showed to you, because we can control the number of layers, carbon, nitrogen, different transition metals. We can control surface terminations. But moreover, again, unlike in graphene or molybdensulfide that's very difficult to functionalize, we can covalently or by electrostatic attraction to negatively charged MXene surfaces bind functional groups, organic molecules, ions, basically graft molecules, or attract ions. Or we can intercalate multi-layer structures to further tune properties of the materials. And nanotechnology is not really about making things small. It's about controlling behavior, composition, properties at the nanoscale. Just to give you an example, titanium 2C is green in reflection, red in transmission, just like gold nanoparticles, but without gold, like colloidal gold particles. But add one layer of titanium and carbon, make titanium 3C2, and situation changes. It becomes actually green in transmission and kind of a violet in reflection. Those are complementing plasmonic color of the materials. Now, let's look at change in surface termination. You replace hydroxyl groups just by, say, annealing vacuum at a couple of 100 degrees C by oxygen on the surface. And the work function goes from 2 electron volts to about 6 electron volts. So if you're looking for material with a tunable work function for electron transport layer for solar cell or LED or organic LED, you can find the material with the right value of the function. You can tune it finely by controlling this surface termination on the material. And what is also important, I already mentioned it, but I want to stress it once again. They can be produced in large quantities. We use this, for example, reactor designed for us by Materials Research Center in Ukraine. They also produce MAX precursor for us, MXene. And you see one of my students, Gita Valoroso, holding 1 kilogram of titanium 3C2 MXene produced within 24 hours in our laboratory. So what it means that it's really scalable. If we can produce 2D material in a lab, and within actually next few days, we delaminated it completely into single layer flakes or few layer flakes in solution. That it means that we can really use it for practical applications, not only for small electronics, sensors, optics, but also for printed devices, for catalysis, water desalination, filtration, purification membranes, energy storage. And there are already first papers even appearing, like for graphene, for introduction of MXene to cement, but actually should behave better because of hydrophilicity things here. Even so, I don't think it's really application justified now. What is also important, processing is simple. We take this colloidal solution of two-dimensional flake in water, no binder, no nothing needed here. And we can basically simply spread it by doctor blading over a surface, dry it, and we get this film. This is, for example, like a 1 micron thick freestanding film of MXene that can be made. It's now on a tape, but again, can be separated. And you can see here all this bubble forms separating from the tape. And it gets strands of aluminum foil and has high conductivity. Again, just colloidal solution in water, spread, dry, you get a film. Imagine, for example, battery current collector with 1 micron thickness instead of 10 micron, because you cannot process metal foil in this thickness. How much it can make a difference in weight and size of our lithium-ion batteries. It's possible because, again, this high negative zeta potential of MXenes, lower than minus 30 millivolt at neutral pH, so it can form stable solution in water. You can see different colors, 3 different MXenes being dispersed in water. If you remember, green solution is titanium 3C2, red solution, titanium 2C. Here. So process is simple. We take ceramic powder, dump it into etching reactor, etch it, make multi-layer MXene clay, we call it when we use water, acidic solution for etching it here, disperse, make colloidal solution, and you can see, for example, here MXene flowing. This is 10-20 milligram per milliliter solution, can be used for inkjet printing. This is a liquid crystalline solution, maybe like 100 milligram per milliliter or more. Our flakes align. This was the one used to make films that I showed to you. And this is showing how we can, for example, make large volumes of colloidal solution in water. Moreover, no additives, no surfactant, stabilizer, binder needed. And depending on concentration, we can basically get different viscosity for processing in different ways, from inkjet to 3D printing, extrusion printing. We can write, fill in pens with MXene, spray coat, spin coat, dip coat, basically use all the known colloidal techniques. One also note, some 2D materials like graphene are stable boron nitride. Some other have extremely low stability. Silicon, germanium, they basically don't survive for a long time in air. Gallium nitride was produced, had to be kept under protecting film of graphene to make it function. A number of MXenes can be hydrolyzed in air, can oxidize those carbides and nitrides at the end of the day. However, if you control defects concentration in materials, achieve materials with high stoichiometry, as we discussed for the first time in this paper in 2021, you can get materials with very, very good stability, which for months is being stored in dilute solution, closed vial, don't really change. You can see Raman spectrum. Single layer flakes for 2 months being stored in a Petri dish and remeasured every week or 10 days. And you see it's still the same MXene. There is slightly higher background, but this is because of a different ensom tip used. And IFM doesn't really show change in the flake thickness here. So it means that it's possible to make stable MXene environmentally stably. Even V2C, the MXene which was initially considered the least stable, we now can keep for months in solution. And when we make flakes, and you see this one will be golden foil if you make here, just by exchanging, for example, initially used tertiary amine with lithium, we get very high environmental stability and also increased conductivity for this material. So message I would like to leave you with here. Huge number of structure and compositions, very wide variety of properties, can be produced in quantity by highly scalable method, can be processed in films, porous networks, aerogels, introduced into metal ceramic matrix composites by processing from actually aqueous solutions. Things here. Now, why are these materials attractive for electrochemical energy storage, water treatment, other devices? This is because they have combination of properties that make them really unique. Electronic conductivity coming from d electrons of transition metal, high density of states as Fermi level, high concentration of carrier. But their surface looks like a surface of transition metal oxide hydroxide. Materials used for energy storage with titanium, niobium, vanadium. Those are all elements that are used in batteries, in supercapacitors, pseudocapacitors. Moreover, they have channels for transport of ions between the layers. And if you want to design materials for energy storage, in particular target what everyone pretty much targets nowadays, getting high power and high energy. So say for electric cars, they can go far, but they can accelerate well, have high power devices, and can, most important, charge quickly within minutes, not within hours, unlike lithium ion batteries today. We need materials which have definitely redox, double layer capacitance won't deliver the amount of energy needed. So MXenes have transition metal. We need materials where there is no solid state diffusion. Solid state diffusion will always fundamentally limit the rate. 2D materials have channels for transport of ions. The entire material is the surface pretty much. But what is also important, what does it mean fast charging? It simply means running very high current through the battery energy storage device. What happens if you run a high current through a poor conductor, like for example, oxides in a battery? Joule heating. Now, MXenes are the most conducting materials for electrochemical energy storage today. I mentioned already an order of magnitude more conducting than graphene. Even you take activated carbon used for electrochemical capacitor, double layer capacitors, or supercapacitors, ultracapacitors. Titanium-32 about an 2 order of magnitude more conducting. Other MXenes will be at least the same conductivity, many will be an order of magnitude more conducting. So what it means, we have all the properties in these materials needed to really achieve the goal of high energy, high power energy storage. Batteries in cell phone, computers, cars that will be charging within a minute or at least a couple of minutes, at the same time storing larger amount of energy compared to electrochemical capacitors. However, it's not that simple. Those are different materials from conventional, as I showed to you before. They behave differently. For example, in some electrolytes, we will get double layer type of storage. You see cyclical tomograms, capacitive typical envelope. In acidic electrolyte, for example, if you take initially aqueous electrolytes, there is initially double layer type of envelope, but at high negative potential, there is clearly redox process happening here. And for double layer, depending on what ion we take in solution, you will see different shapes, cyclical tomograms, different capacitance value, because these different ions will come closer to the surface or stay away from the surface salvated. Lithium, sodium come close to the surface. They can charge, basically there is overlap of electron clouds, they can transfer charges. Some other elements, cesium, magnesium, will stay away from the surface, for example, between MXene layers, salvated. As a result, amount of charge stored will be smaller compared to ions that can come to the surface, transferring charge partially, at least polarizing the surface. What is also important, I try to convince you that these materials are good for high rate energy storage. And going back to titanium-32 in protic electrolyte, sulfuric acid electrolyte, you will see this capacitive envelope, but then broad but very symmetric initially, up to 100 millivolts per second. Typical supercapacitor rate, this redox is absolutely symmetric, less than 20 millivolt separation between the peak. But even at 100 volts per second, 10 millisecond charge discharge, you can see it is still redox. So what it shows, it's possible to have redox energy storage, high energy storage, at extremely high rate. We're not limited by rate of redox process. We're limited by transport. That's why when we go from thin film to thick electrodes, we lose somewhat in capacity, in charge storage. And it means that we need to design architecture in addition to having high rate redox materials. So electronic conductivity was really limiting the factor so far for other materials. That's why you cannot do it with oxides, for example, the same charging. And again, we know from X-ray absorption spectroscopy is reversible oxidation reduction of titanium atoms in the surface here. Now, if we take non-aqueous lithium electrolytes, lithium TFSI, for example, and look not at different ions, even at different solvents, again, you will see differences, drastic differences in shape of cyclical tomograms. And if you take lithium TFSI in DMSO, solvent which was used in the first generation of lithium-ion batteries, you will see that when we charge and discharge it, X-ray diffraction shows us there are variations, expansion, contraction of the lattice, and a large interlayer spacing. With a layer of titanium 32 being less than 1 nanometer, we have like a 9 angstrom, almost 1 nanometer of something, electrolyte between the layers. Take a cetronitrile, and the spacing is smaller. Now we have just about 3-4 angstroms of electrolyte between the layers, and much smaller changes in lattice spacing, basically spacing between the films. But now with propylene carbonate, there is no variation of spacing as we charge and discharge, and just a little bit more than an angstrom between MXene sheets. Why does it happen? Because in case of propylene carbonate, we have complete desolvation and only lithium ions go between the layers, while in case of, say, DMSO, we get solvated lithium ions, we get lithium ions on the surface, lot of electrolyte, and we have this variation of spacing. Very good actually for electrochemical actuators, almost doubling the space between the layers, large deformation, large actuation, but definitely not for lithium-ion battery, where propylene carbonate appear to be the right solvent. So we need to find the right ions, we need to find the right solvent, we need to select from huge number of MXenes. However, if we do it right, we should be able to get everything from double layer capacitance for very fast discharge, for example, very long cycle life, to pseudo capacitors, partial desolvation of ions, to complete desolvation and intercalation between the layers of naked ions. I'm not going to give you recipes how to design an energy storage device. What I want to show you is that this new family of materials allows you to pretty much select, tune for application requirements. And of course, whenever you work with low dimensional 2D materials, you also can take advantage in geometries that conventional materials cannot give you. For example, have printed my fabricated interdigitated devices here, actually more than 100 devices on a silicon wafer for very high rate operation, like a CDC conversion at 120 Hertz, competing with, say, electrolytic capacitors, but having much smaller size and larger capacitance. We can make flexible devices. We can incorporate MXenes into fibers and make pure MXene fibers and make knittable or printable on fabric energy storage devices, combine them with sensors, with antennas for communication, for example, or charging, remote charging, and so on here. Also, there are many other useful properties being explored by the community. For example, suppressing dendrite growth, enabling lithium, but also sodium, potassium, zinc, metal batteries. Lithium grows in a planar way on MXene, unlike copper. And again, unlike copper, this black traces here, which leads to dendrite instability, one can get stable function, stable deposition dissolution of lithium over 100 cycles. And as a result, it's possible to use it for electrodes, current collectors of metal batteries, not only metal ion batteries. You can make this much thinner current collectors compared to copper or aluminum for cathodes and anodes of batteries. One can use it as binder instead of graphite and carbon nanotube for silicon or NMC or carbon. So I think you get the idea. There are other applications being explored, for example, lithium sulfur, sodium sulfur, potassium sulfur batteries. It's in addition to suppressing dendrite growth on the anode side. MXenes conducting, they compensate for low conductivity on sulfur, they can absorb polysulfides, prevent their transport through separator, and also catalytically decompose those. There are applications also beyond energy storage, and I think I'm already running out of time, should finish, in harvesting. From solar, for example, I mentioned electron transport layer, but also to humidity, salinity gradient, electrokinetic, piezoelectric energy harvesting, triboelectric, thermoelectric, and others. Some MXenes have a wide voltage window in aqueous electrolytes like titanium 3C2. Can be used for aqueous supercapacitor and battery electrodes, but some others pretty narrow. What it means? They will be good materials for hydrogen evolution reaction, water splitting. And this is again all about designing the right composition. You see, over potential for water splitting can range from minus 1.4 to very close to platinum, close to zero. Moly2C, for example, has been predicted to be a good one. And indeed, it shows much better performance than titanium 3C2. But it's still not at the level of, say, platinum. However, if we incorporate single atoms of platinum into point defects, basically replacing some of the transition metal atoms in the surface of MXene, we can get material with single atom platinum with very small amount of platinum added, but performance now matching platinum on carbon with a much larger loading of platinum things here. So again, you can design with these materials, and this is the key advantage of them. Many electrochemical applications of MXenes have been explored over years now, from supercapacitor to organic lithium sodium ion capacitor, pseudocapacitor, hybrid devices, pretty much all kinds of batteries and hybrid energy storage, but also on-chip, textile, basically working on morphology, flexible, transparent devices, things here, printable devices. Also passive element, current collectors, binders. And you can use MXene and other related technologies, capacitive ionization, electrocatalysis, implantable electrodes, electrochromic, plasmonic actually electrochromic devices, and so on. But my time is over. I used my 45 minutes for the presentation. What I wanted to summarize at the end. We have this large family of two-dimensional materials which add to graphene, oxides, chalcogenides already available to us. They can be used in electrochemical applications. For example, supercapacitors, batteries. They can be produced by scalable etching methods in kilogram quantities, potentially, of course, can be scaled to ton quantities. Can be processed from pure water into a variety of morphologies. I didn't go today, didn't show you aerogels, hydrogels, fibers, and so on. But naturally, you can read papers on graphene, and you can do exactly the same thing can be done with graphene oxide. Virtually unlimited choice of composition structure, it means properties, tunable, programmable, ideally, properties here. And whenever you think of need for high conductivity and redoxability, those are MXenes, because they have higher conductivity than reducing graphene oxide, and they offer redox ability, reversible redox of transition metal oxides, hydroxides here. Also, you can make current collector free devices, because if you use MXene as active material, typically you really don't need metal current collectors. Or you can use MXene as current collector on binders. And where also you need to look at here, where are limitations, where are strengths. For example, porous carbons, activated carbon, carbide-derived carbons, graphene will have highest specific surface area. So volumetrically, MXene win. Gravimetric, double layer capacitance, carbon will do better because it has larger specific surface area. So you need to select MXenes and use them where they can give advantage. They're denser volumetrically. If you're looking for a small battery, for example, for cell phone, you win. If you're looking for a battery for stationary storage, large, inexpensive, maybe lower performance but cheap, it's something else. If you look for a flexible device, flexible battery, conformal, one you can embed into your clothes, MXene are advantageous. So again, select the right system where it's needed here. And of course, like in any new materials, there are challenges. We need to widen the voltage window in aqueous system to increase the total energy density. Having so many materials, so many compositions, structures, surface termination, and we can also tune defects, do defects engineering, flake size, alignment of flakes. It's a blessing, but it's also a curse at the same time. How do you select the right one? How do you select? I showed you how, for example, ions or solvents even can affect the performance. How do you select the right one? Here, enormous amount of modeling simulation should be done, that machine learning and artificial intelligence can be used to select the right material, electrolyte couple, optimize the materials. We're not there yet, but computational techniques develop very quickly and should match our experimental progress soon. And of course, there are applications beyond energy storage and harvesting for MXenes, including, for example, electromagnetic interference shielding, antennas, communication, 5G, beyond 5G, printable antennas. Medical applications, from DNA sequencing to adsorption of urea for wearable kidney to implantable epidermal electrodes, skin electronics, and so on. Gas sensing, electrochemical biosensing, optoelectronic, plasmonic devices, water purification, gas separation, adsorption, removal of heavy metals from solutions, many others here. And industry is speaking slowly. There is a MXene Association. You can go to this website, register, get free newsletter every week or two. And the goal is to bring commercial manufacturers and users with research community together. And this was my very last slide. Option I've done, showed to you in MXene, was done not by myself. This is a result of work of large and very productive research group. This is my Nanomaterials group, picture taken already half a year ago. So there are some new people, there are some people who left, graduated, got jobs. For example, Armin left for battery industries, talking about energy storage just a couple of months ago. We also work with many people around the world. Patrice Simon from Paul Sabatier University has been my collaborator for many years. There are strong group, Doran Auerbach's group, and Bar-Ilan University, many other colleagues in the US, abroad, contributed to research on MXenes we do. And we also have been supported by a variety of US and international funding sources, also by industry, first of all, Murata, Japan, which licensed multiple patents from Drexel. And with this, I'm going to stop, and I will be glad to answer questions. Thank you.
Thank you very much, Professor Gogotsi, for this inspiring speech. So there is a lot of things to do with the MXenes, and
Absolutely.
it's very exciting research field, and also as an exciting material, we have a lot of questions here for you. So the first one, actually, Roselito Andrade. He's thanked you to introduce him to Mr. J.R. Miller. So he made a lot of questions, and the first one is this one.
Can you read it? I currently don't.
All right, sorry. Why MXene has a small stable potential window? Is there a way to make this window larger, about 1.7 volts, for instance?
Well, potential window is a function not only of the material, of course, but also electrolyte. When I showed it, for example, this here or previous like a cyclical tomograms, those are potential windows, say in protic electrolyte, acidic here. If you take, for example, water and salt electrolyte, I have here an extra slide. You can increase the voltage window in, for example, 19.8 molar lithium chloride to about 1.6 volt. So yes, short answer is yes. You need to select MXene, but also it depends on the electrolyte, of course. So in aqueous electrolyte, but saturated or water and salt electrolyte, you can certainly have a wide voltage window.
Okay, thank you. There is another question from Roselito. MXene is a good candidate to low-cost supercaps. And what about high-power supercaps?
Yes, definitely. Because what I mentioned, power is about current, conductivity. So what it means is if you have materials which is more conducting than activated carbon used and more conducting than carbide-derived carbon used, say, by skeleton technology or graphene, you definitely can get very high power. So a short answer is yes.
Yeah, I have another question regarding the cost. Is MXene expensive? How can we compare MXene with, for example, carbon materials? I don't know any. I don't have any idea of price, for example. Can you give us a perspective?
Yes, it is expensive. And reason is very simple. It's produced in small amounts only. However, fundamentally, there is no reason why it should stay expensive. It's economy of scale. Let me remind you, aluminum metal, when it was first made more than a century ago, it was an exotic metal that Napoleon III made silverware, forks, knives, and was serving aluminum instead of gold or silver to most significant guests at French royal court. My father has a medal of London Fair from 1905 made of aluminum. Now it's one of the most common metals. So as long as there is a precursor, titanium, carbon, what I told to you, are very abundant precursors. Nitrogen, the same. We can produce it by etching, wet chemical etching, molten salt etching. Recall, aluminum metal is produced from molten salt electrochemically at much higher temperature. So it means that it can be scaled to be produced at low cost. Definitely can compete with reducing graphene oxide in cost here. However, at the moment, while it's produced in small amount, it's still expensive. So we need to start with smaller volume application where it gives unique advantage. Something you cannot do with other materials, like, for example, catalytic, electrocatalytic application, current collectors, flexible, printable devices, before it can go to, say, car batteries.
Okay, thank you. We have another question from Julian Fiatis. She thanks you for the inspiring talk, and she asks, have you tested any type of dipiotetic solvent electrolyte with these materials for energy storage applications?
I didn't get the first part of the question. Have you tested what?
Any type of deep eutectic solvent?
Okay, dipiotetic solvents here. We made an attempt. We did not continue because, well, my postdoc started to work on this, left and became a professor at Delft University here. There are a couple of papers, but very little has been done. I think no reason why not.
Okay, thank you. We also have another question from Abner Sampaio. He thanks you for the amazing talk. And he asks, is there an efficient way to intercalate anions into MXenes?
Well, that's a very good question here. We primarily because of this negative charge of MXenes. Cations, protons, they easily go even spontaneously between the layers. You can get them here. For a long time, we believed that cations could not be well intercalated here. We know now it's possible to get also cations in, but you need to have some special cations having charge transfer. You can get cations when they're basically pulled by, anions, when pull the cations here, or you need also to expand the lattice. MXene basically having bridging molecules between the layers that would allow anions go in. So definitely cations go more easily and readily into MXenes compared to anions, but we know actually nowadays that anions can also get into MXenes.
Okay, thank you. We have another question here from Hugo Lemos. He thanks you for the presentation and asks, what are the strategies to avoid MXenes oxidation in aqueous solution or water-based inks?
Well, basically, strategy is simple. First, you need to start with oxidation stable MXene. What decreases stability? It's a non-stoichiometry. Many carbides and nitrides are non-stoichiometric, so you need to pay attention to having, for example, really titanium 3C2, not titanium 3C1.6. We published just like about a month ago a paper in Nature Nanotechnology on SIMS analysis of MXene that shows that some sample of max phase precursor and MXenes may contain up to 30% of oxygen in the carbon sublattice. Those materials are stable. These samples I showed to you were produced using highly stoichiometric max phase, titanium 3C2, and stability increases dramatically. But also, point defects on the surface. You overage your material, you get a lot of these vacancies, which I showed can be used, for example, for electrocatalysis, but they decrease stability in water. Larger flake size, fewer edges, more stable MXene again. So stoichiometry, defects, flake size, those are key parameters. But there are also surface terminations. Some of them improve stability, some not, because they can be hydrolyzed, things here. And if you store it for a long time, store it just like a perishable food you buy in a refrigerator, away from sunlight, and higher concentration of solution. Less water is available for hydrolysis. For a longer time, you can store MXenes. And one more trick. Naturally, M2C MXenes, Cine 1, are less stable than the thicker one. So titanium 3C2 will be more stable than titanium 2C. Niobium 4C3 will be more stable than niobium-2C because of thicker structures here. So as you see, there are many different parameters that determine stability, but it's possible to store material in solution for a year or longer. Definitely films that you produce can stay for many years. Remeasured conductivity of films made years ago, and they're still highly conducting. And some o-MXenes are more stable than other MXenes.
I see. We have a time for another question, but I just want to make a comment. Um, I think there is a compromise between the thickness and, for example, if we think about electrode, the surface area for electrode with thicker materials, you have a small area.
Correct.
So maybe the you have a compromise between the stability and also the performance of the material for energy storage, for example.
You are absolutely right. So if you are talking about, first of all, capacitive, pseudo-capacitive energy storage, materials with thinner layers like V2C will give you larger surface area and larger, basically, surface-based storage here. And thicker, heavier layer like niobium-43. Layers with also heavier element like, say, tantalum. They certainly will give you lower gravimetric storage here. So that's absolutely true. And that's why you really need to engineer, select the right material for application. There is no like a single MXene that fits all application is the best in all applications here. Depending on what you want to achieve, it's important. Just like defects I mentioned. If you want to make ink for inkjet printer and sell cartridges with ink which will last for a long time, you want a highly stable MXene. But if you make MXene for catalytic application in reduced environment like hydrogen evolution reaction, actually surface defects, point defects will improve performance of your material. So in one case, you want to have no defects, or for high mechanical properties, no defects. In other application, you want to have point defects on the surface.
Yeah. Yeah, our time is finishing, and we have a lot of questions here in the chat. We are not
Mhm.
we cannot go so
Forever.
far.
I understand
Yeah,
it. Let me
we
just
cannot.
also show you this my website, nano.materials.drexel.edu. I think if you go there, you will find answers to some of the questions, and you will certainly find my emails and email of people in my group who may be, in many cases, more knowledgeable even than myself, who can answer your questions. Moreover, something I forgot actually to show you. We teach several times a year a course on MXenes. The next one will be during the third week of February. We have like entire week for 5 hours a day dedicated online to covering all aspects from synthesis to characterization to electrode processing and electrochemical application of MXenes. If you want to learn more, don't hesitate to sign up for this course and take a course on MXenes to learn more about these exciting materials in February.
Yeah. So thank you very much for giving us this opportunity to attend this course. And I have to finish here. And so I would like to thank you very much for your very nice talk and also the inspiring material that we have to learn a lot to have a better material for energy storage and other applications. So yeah, just um, the last sorry, I forgot the forgot the word. Um, We will continue this Cine webinar next year, so people in the crowd, please stay signing up with Cine and to have more feedback for the next presentation. So thank you very much again for your presentation, and also the people in YouTube. The questions that we couldn't make here can be done directly in the website of Professor Gogotsi, or just we will send him the questions, and we hope that Professor Gogotsi can reply us.
I'll
So
be glad
thank you
to
very
address
much.
any further questions. Thank you to Cine, and thanks to everyone who listened today.
Bye-bye.
Goodbye.